So, good evening, everyone. Today we'll start our live session 6. The course instructor is Professor Swarup Bag, and I'm the teaching assistant Ankur Kapre. And we'll start now this problem solving things. So, first we'll wait for some time if somebody will join. Okay, so now we'll start our session. So, here the question number 1 is here. This is asking for slip to occur in polycrystalline materials, how many independent slip systems are required? So, as we know, an strain matrix or matrix have 9 components, which are 9 components, which are, suppose for strain matrix, it will be sigma 11, sigma 12, sigma 13, sigma 121, sigma, sorry, epsilon. Actually, wait, I should not write like this. For a strain, we'll just see here itself, strain components, epsilon 11, epsilon 12, epsilon 13, epsilon 22, epsilon 23, and epsilon 33. Also possibility is there, epsilon 21, epsilon 31, and epsilon 32. So there are only total 9 components. In that, only if it is symmetric, then this epsilon 1 2 is equal to epsilon 2 1, epsilon 1 3 is equal to epsilon 3 1, and epsilon 2 3 is equal to epsilon 3 2. So this is also possible while it is symmetric. So in polycrystalline material, it is like we know that it will be symmetric. So and due to the volume concentration during plastic deformation, this will be like this. This will be this one, sigma epsilon 1 1, sorry, plus epsilon 2 2 plus epsilon 3 3 is equal to 0. So there will be total 5 independent slip systems, 1 2 3, 1 2 3, and the another 2 will be from here. Okay, so this matrix, this independent quantities will be uh, requires for the slips to occur in the polycrystalline materials. Okay, so total number of these is 5. So answer number 1 will be correct option. Okay, for question number 2, they're asking if the stress to cause slip is very high, such as critical resolved shear stress is very high, then which of the following statements is true? So there is written already this CRSS is very high. Okay, so as we know, first option is the fraction may occurs before slip. Like in brittle ceramics, ductility becomes high. This dislocation density increases dramatically, flow stress becomes high. So there will be a straightforward answer that will be fracture may occur before slip, like in bitter ceramic. Okay, so this will be the correct answer. Okay, now Which of the following statement is true? So the option number 1 will be true. Now the question number 3, favoring of easy glide is promoted by. So see here, low degree of crystal perfection. So that means it will it will lead to defects. It refers to defects. Okay, defects. There will be two possibilities. One is higher number of these atoms or lower number of the atoms, like vacancy. And because of higher, it will cause the hindrance. Hindrance is favoring of easy glide. Okay, hinders. While if it is low, then may be possible easy glide. Okay, then temperature they are talking. So this option won't be correct because low degree of crystal perfection is it won't promote because there will be two possibilities and in high temperature. So as we know that according to the critical resolved shear stress CRSS and temperature, the spot will be like this. It means that while the critical resolved shear stress is increasing, temperature should be low at lower temperature, or temperature we are increasing, so CRSS will decrease. So that means it is also not possible. Easy to glide promote. Okay, then the species single crystal, it is also not possible because there is no easy glide is promoted in that crystal system, and HCP is the final answer, will be the final answer. The question number 4, Smith's law predicts. So options are the elastic perfectly plastic behavior of the crystal of a crystal, only elastic behavior of crystal, perfectly plastic behavior of a crystal, smooth tension from elastic to plastic behavior by a power law. So the option number C will be the correct. Perfectly plastic behavior of a crystal. That is predicted by Smith's law. So question number 9. Here the Smith factor M has a maximum value of, they're asking M, maximum value. So as you can see here this formula, first of all, the tau of critical resolved shear stress is equal to sigma y cos phi 1 cos phi 2. Cos phi 1 and cos phi 2 are the value that is called Smith factor, that is equal to m. So here phi 1 and phi 2 is read, we can write down like this. Okay. These angles are known as phi 1 and phi 2. So if we'll consider one angle as a this, the angle between tensile force and slip direction and plane normal. In these three, we have to tensile force and plane normal, one angle will be theta 2, and tensile force and slip direction, the another angle will be theta 1. So this two angles, if we'll consider A, this angle phi, instead of A, we'll take phi. Phi is equal to 0, phi 1 is equal to 0, and phi 2 is equal to 90 degree. So phi 1 is equal to 0, so we'll keep these values in this formula. So we'll get cos 0 plus, sorry, not plus, it is into cos 90. So it will be 1 into 0, is equal to 0. So m value will be 0. So the maximum value when it will come, when we are taking this phi 1 and phi 2 both equal to 45 degree. Okay, and then m value will be cos 45 cos 45 1 by root 2 1 by root 2 1 by 2, that is equal to 0.5. The maximum Smith factor value m will be equal to 0.5. So the question number 6, consider the following reaction between parallel direction, sorry, dislocation. E in each case, determine which of the following reaction is energetically favorable. So for that, what we have to do, we have two conditions, energetically favorable and energetically unfavorable. So for energetically unfavorable and favorable, the energy will be like this. For favorable, it will be the change, sorry, the change in energy is less than 0, where is favorable. And if it is greater than 0, then it is unfavorable. Okay, so how we can find out these things? First, we have to find out the resultant. Find the resultant vectors. So what are those? This option. First, we'll find out for this. So for this, so here you can see, if we'll do just a resultant vector, what it will be a by 2, and both will add. So the vectors will be 1, not 1, it will be 2, and the second one will be 0, and the third one will be 0. Okay, and okay, just like that we'll write. For second, it will be a by 2, 1, 1, 0, and for third one also We'll just write down A by 2 2 minus 1 and 1. Okay. So now what we have to find out now, to find out the energy unit length, energy per unit length of dislocation. So second one is energy per unit length of dislocation is G B square. We know. So we don't have to find out this one. We have to find out uh, the change in energy. That will be B final GB square final minus GB square initial. But we know that G there are like both places it is common. So we'll just neglect that. So what we have to find out, just have to find out, because we only want this, is it lesser than 0 or greater than that 0? Because J is a positive, so we'll just find out. So del E is equal to B final minus B initial minus B square initial. So B final, what is that? B final is like this one. First option I'll just try to calculate. Hello. So we were here. We were trying to calculate this part. So the energy, energetically favorable or not, we'll check. So for that, this value will take from here. The final will one value will be this one. So for that, we have to take like this A2 square upon 4 into 2. Okay. Then minus this values, two values, we have to reduce from this. First is like A square upon 2 root 2, not root 2, it will be like after. First I'll write like this, then it will be good. 4 root 2. This also will be, no, this is like square. So here also square plus A by 2 root 2 square. Okay. Now we have to reduce. I think I'm keep doing some mistakes here. I'll just cross check once. Yeah, here. This value is 2 and this is also 2. Okay. So after calculating this, it will become 0. So this option, this one value, it won't be favorable or unfavorable, we can't consider. So we'll just neglect this one. Second one we'll have to calculate like this, same. So first we have to keep the values same as it is. So I'll just take extra page here. So here you can see a by 2 root 2 whole square minus bracket a by 2 root 2 whole square, not this square, minus a by 2 root 2 square here. Okay. So what will it will come? It will come like the answer will become like a square by 2 and it will be in minus because negative value here, two negative values are there and one positive. After they cancel out, it will be negative. So the energy will be lesser than 0. So this is favorable. So option 2 will be favorable. Which one? This is favorable. We can't have this here. Okay. We can use that. This one is favorable. It is coming uh, less than 0. Then the next one here a by 2 and the value will be like 6 whole square minus a by 2 okay. Then a by 2 root 2 square plus a by 2 root 2 square like this. Okay. Now the value will be like for this while calculating it will come around positive something like this will be a by 2 a by 4 36 a by 4 2 and 2 4. So let's just cancel out. Okay, that is a positive. So the answer for this, it will be not favorable. Del A is greater than 0. That is unfavorable. Okay. So the option, only two option number second is possible. That is the last one. Now we'll consider the question number 7 here. They're asking, consider the dislocation dissociation reaction A by 2 110 is greater or equal to, oh no, sorry, it is written as a by 6 211 bar plus A by 6 121 in an FCC crystal. Assume that the energy by length of the dislocation of a dislocation is given by EL is equal to GP square, and neglect any displacement if the energy on the edge versus screw nature of the dislocation. Assume that this reaction occurs and the partial dislocation move very far apart. Neglect the energy associated with the stacking fault between the partial dislocations. Express the total decrease in energy by length of original A by 2 1.011 dislocation in terms uh, of A and G. And second option is the second they are asking, on which 111 must this these dislocations lie. Okay, so they are asking two things. So here they're asking express the total decrease in energy by length of the original A by 2 011 dissociation in terms of A and G. So for that, what we have to do, just we have to consider this value like this. Uh, we have to divide in by A by 60. So for that, what we can do, A by 2 0 1 1 A is A by 6 1 bar 1 2 plus A by 6 1 2 1. So we have divided into two parts. Now we'll just check the energy decrease, that is del E, and how we can check, like, sorry, we have given already. First we have given the dislocation energy by length, and energy by length is like EL by GB, EL is equal to GB square. It means that EL is equal to GB square. It means G we have to consider as a common, and we have to just decrease. You know that formula G B final minus B initial, so we'll just keep this one as a B1, B2, and B3. This values, okay? So B here, B final will be B1 square of this mod of B3 square minus B1 square mod. Like this we have to do. And that also this B2 square, how we can calculate? So we have already calculated last time. So it is like easy only. You have to take A upon 6 and root 6 whole square plus A upon 6 root 6 whole square minus A upon 2 root 2 square. And in the last you will get a G will be there. So in the last you will get G upon G into A by G into A square by 6. So there will be one option is there, two option is there. Okay. And the second option, second things they are asking on which 111 must this dislocation lies. So for that, we have to add on one plane 111 on that, on which must this dislocation lies, which this one A by 2 0 1 1. Okay. So we have to just calculate the angle theta. cos theta should be 0 because it is lying on that. So theta will be 90 degree. So what is that? With 90 degree. We can calculate like this. 1, 1 bar, 1 will take from here. And 0, 1, 1 will take from this original uh, test location there. Okay. So if we'll calculate, if we'll multiply, then we'll get theta is equal to 90 degree, or we can say cos theta is equal to 0. Okay. So the final answer will be option number 1. In question number 8, here we have to assume that result shear stress of 1.6 megapascal is applied to a crystal and causes dislocations to pile up at a precipitate particle. Assume that the shear strength of a particle is 7.2 MPa. What is the largest number of dislocations that can pile up at the precipitate before the yields? Okay, so they are having they have given one is resolved shear stress, or we can say applied shear stress. Applied shear stress is equal to tau, and tau F is what? That is shear strength. And what is N? N is the largest number of dislocations. Number of dislocations piled up. So just we have to put the values. Here the tau is given as a 1.4 megapascal. Tau F is given as a 7.4 megapascal, the strength, and N we have to find out. So the formula it will modify. So the N will become TF minus tau f minus tau upon tau, 7.4 minus 1.4 upon 1.4. So if we'll calculate, it will come n is equal to 4.2. And what they are asking, what are the largest number of dislocations that can pile up at the precipitate before it yields? So the first things, number should not be the fractional, so it won't be correct. The second thing, this is nearest to the 4. So it could be the option number would be 4. Correct answer should be 4. Now the question number 9, they have asked or one so that the shear strain rate is given by gamma is equal to ay gamma by dt is equal to rho b u bar, where rho is the dislocation density and u is the average velocity of the dislocation in a test. In a tension test, the tensile strain rate is half of the shear strain rate if the Schmidt factor is 0.5, otherwise it is lesser than the otherwise this will be like epsilon is less than half of gamma. In a typical tension test, the cross-head rate is 0.2 inch per minute and the gauge section is 2 inch in length. Estimate u bar in the like average velocity in a typical tension test for a typical method with an initial dislocation density of 10 to the power 10 per centimeter square. Take Berger vector as 0.255 nanometer. Okay, so first they have given, what they are asking first of all, this u value they are asking. What is the average velocity? And they have given the various options here. So, and we know that how we can find out this strain rate. Okay, so strain rate we can find out by cross head velocity by gauge length. So cross head velocity, how much they have given? Here they have given 0.2 inch per minute. So we'll just divide by 60 since we want in centimeter per centimeter. Okay, and the length is gauge length is 2 inch. So inch, inch, and 1 by 2 second. So it will be per second. Okay, so strain rate will be like We'll calculate like this. After that, what we have to calculate? They have given the formula, that is uh, the strain rate is equal to 1 by 2 shear strain rate. Okay, strain rate is equal to 1 by 2 shear strain rate. So here we can find out the shear strain rate. That will be around 1 by 2 into 0.2 by 120. Okay, and in the last they're asking they have given this formula equation, that is the shear strain rate is equal to rho, the density, dislocation density, P, that is Burgers factor, and U bar we have to find out. So how we can find out? U bar we have to take it like this. Rho they have given already, 10 to the power. Since they have given everything in millimeter, so we'll just convert the centimeter into millimeter. So 10 to the power 10 to the power 8. Sorry, first you have to find out. First we have to keep gamma value. Then we have to divide rho and b. So what is the gamma value? That is around 0.1 by 120, or we can say 1 by 12 into this rho value which they have given. So 1 by rho value, how much they have given? 10 to the power 8 in mm. Mm will go up because it is in the per mm, sorry, mm square. Then Burgers value they have given in nanometers, so 0.22255. Here already it's in second, and this is in nanometers, so we have to multiply with 6 mm. Okay, 10 to the power 9 meter. 6, not 6, it will be 7 centimeter. So it's okay. Yeah. So it will around 10 to the power 6 mm into minus 6 we have to do. Then after this calculation, we'll get the value that will be around approximately this 0.13 into 10 to the power minus 3 mm per centimeter. Oh, sorry, mm per second. It is rate. So velocity. Okay. Then the question number 10. And question number 10, it is given consider the following BCC dislocation reactions A by 2 1 bar 1 bar 1 is equals to 1 by 8 1 bar 1 bar 0 plus A by 4 1 bar 1 bar 2 plus A by 8 1 bar 1 bar 0. So first is identify whether the reaction will occur or not. First we have to identify. Then what kind of crystal imperfections results from the dislocation reaction. From this dislocation reaction. So first we have to find out is it reaction is possible or not. So for that, for condition of the splitting, it should be like this. It should be lesser than 0. The final values like this is we can say B1, this is we can say B2, B3, B4. So all this addition and this substitution should be like lesser than 0. So for that what we have to do? So after calculating it will be like keep the values A by 8 root 2 square plus a by 4 root 6 square plus a by 8 root 2 square minus a by 2 root 3 square, and after calculation it will be like it will come lesser than 0. So the option number reaction is possible. Both will be answer correct. Then after that, here you can see there it is a BCC dislocation reaction. So stacking fault energy also possible. So the option number, this one is correct, not this one. Okay. So these two are neglected before itself, and the last option is a reaction possible, and a stacking fault will be there. Okay. So this was the last question of our today's lecture. And in previous lecture, I actually explained one question wrong. This is this one. So here the energy associated with the surface defects and the maximum for aluminum is due to grain boundary. It will come the answer, not twin bond, not like stacking fault or twin boundary. Okay, twin boundary is associated with the stacking fault, but not here. A stacking fault is not applicable. So the grain boundary is a region. And the question number 12, in BCC iron, a tensile stress of 52 megapascal is applied along 010. The critically resolved shear stress will be this. What is that? We have to find out. If slip occurs on 110 plane in 1 bar 1 direction. So first thing is that we know that critically resolved shear stress is tau C R S S, okay, is equal to sigma 0 into m. And as we know, what is this? Sorry, this is already, this is we have to find out. Tensile stress, this is already given, this 52 megapascal. And m is nothing but the Smith's factor, that is cos phi 1 cos phi 2. Okay, so how we can find out this cos phi 1 and phi 2? The angle between the load applies, this load applies, and the direction of outward normality, that is that uh, uh, we can find out the phi 1 and this load direction and the slip direction, the angle between those we can find out the phi 2. So phi 1 will be like cos phi 1 will be 1 by root 2, and cos phi 2 will be 1 by root 3, and the multiplication of this is 1 by root 6, and we'll just divide we'll just keep CRSS is equal to 52 into 1 by root 6. So the answer will be approximately 21.22. Okay, thank you so much for joining, and for further doubts will be available on the next Saturday. So please join at 6 to 9 p.m. So 6 to 8 p.m. Thank you so much.